there's one factory with 200 employees. And 160 are female. Okay? And choose 25 persons from this factory. Okay? S is the number of female in this sample. So we are going to ask some questions here. First one is the probability distribution of S. The second one, what is the probability that female will be at least 0.8, so that is 80% in this sample. And the third one, what is the probability that female will be less than 60%. The fourth one, all the same, we are talking about the probability of female, and so this is the proportion proportion of female is between 0.68 and 0.92. Okay, so basically this is the application of the theorems that we just talked about before, because we are going to talk about the sample sum and sample mean distribution. The difference is that in this case it is a proportion, okay? And basically that's the binomial distribution, okay? So first we know there's a total of 200 persons, okay? 200 employees in this factory, okay? And in this factory there are 200 employees. 160 are female, okay? 160 of them are female. And now we are going to choose 25 persons from this factory. So the sample size is 25, okay? The sample size is 25. And so in this case, S means the number of female in this sample. So let us say we choose 25 from this employees, from all these employees, and S, okay, we choose only 25, and S is the number of female, okay? So in this case, what is the probability distribution of S? So it should be F, okay, S. How many people do we choose from this sample? How many do we choose? We choose 25, right? We choose 25 people. And of course, this is either or. Either this person is a male or this person is a female. What's the probability that this person is going to be a female? Because the total is, okay, the total is 200, right? And how many people will be female? The total is 160. So in this case, what's the probability when you choose one person from this group? What's the probability that this one going to be a female? 0.8, right? 0.8. So we choose 25 from them, and we are focusing on the number of female, and the number of female is S, right? So among these 25 people, say, what's the number of female? That's S, right? S. And so if this is the number of female, then this is the probability of being a female, right? And then of the person being chosen is a female. And then this should be to S power. And this one is the number of male, right? Because it's either or. Either this person is a female or male. So if the number of female is S, what about the number of male? It should be 25 minus S, right? So this is the answer for the first question. This is a binomial distribution, okay? Because there are only two choices. And in this case, how many experiments you have done? You do 25 times, okay? You choose 25 people from this factory, okay? Any questions? Okay, then the second question is, what is the probability, okay, that the number of female, okay, the number of female will be, the probability of female will be greater than 0.8, okay? So now let me ask you this question, right? We have 25 people, okay? We have 25 people. If among these 25 people, I only got 2 female, okay? I only got 2 female. So what's the probability, okay? What's the proportion that I got this? Because there is 25 people, right? There are 25 people, but I only got 2 female. So what's the proportion here? The proportion is 2 over 25, so that's equal 0.08, right? But you know, as a matter of fact, in this factory, what should be the probability of female? It should be 0.8, right? It should be 0.8. But in this case, how many do I get? I only get 2 female. So what should be the proportion or probability? It's only 0.08. Of course, you know this one is not equal to that one, right? Because this is a population and this is a sample, okay? So sample proportion or sample probability will be different from what's going on in terms of the population, okay? So these two will not be the same, okay? So in this case, what we are going to find? We are going to find out that what is the probability? It should be at least, the proportion should be at least 0.8. So what does that mean? That means, in this case, there are 25 people, right? I need to find out what's the proportion, what's the probability that this size, okay, the size of the female, okay, when I get this, it should be at least be 0.8. That is 80%, right? So what does that mean? That means, okay, I got 25 people, right? 25 people is all I get. And of course, I need to find the number of female in this case, okay? And then this number should be greater than or equal to what? 0.8, right? This is what the question tells us. This is the number of female, right? And this is the number of the sample. And I want this number to be greater than or equal to what? 0.8, okay? So what does that mean? At least I have to choose 20 people, right? At least the number of female must at least be 20, okay, or 21, 22, 23, 24, and 25. It all works because in that case, it is greater than 0.8, okay? So what does that mean? So in this case, you have two ways to deal with this problem, okay? The first one is by binomial distribution, okay? The first one is by binomial distribution. So let us see what's going on there. Okay, because the question asks what's the probability, okay? There will be more than 80% of the sample will be female, okay? And so we figure out if the proportion of female in this sample is greater than 0.8, what does that mean? That means when we choose 25 people, right, at least 20 people of them should be female. It can be 20, 21, up to 25, right? So because in this case it is a binomial distribution, so we can do it like this, okay? So P S greater than or equal to 20, right? Because this is what we intend to find, right? This is the number we intend to find. This one is exactly equal to S, right? But this one we have to get something that is greater than 20. So in this case, we use the summation sign, okay? So this is equal to 20, and from 20 to 25, okay? And this is the same thing because we choose 25 people, right? And among these 25 people, the number of female is S. And this will be equal to 0.8 to S power and 0.2 to 25 minus S power. So this is one way to deal with this question, okay? Because it is a binomial distribution. So we are looking for the number of female is equal to 20, 21, 22, 23, 24, up to 25, okay? So this is the way to deal with it. Okay, any questions? Okay, then we get to the second one, okay? The second one is what's the probability that female will be less than 60%, so that's 0.6, right? So we want this. S divided by 25, that's the proportion, right? It has to be less than or equal to 0.6. So what does that mean? That means the number of female must less than or equal to 15. Sorry here, because it said less than, right? If it is less than, so it is only this part, okay? Less than, okay? Less than. So it should be less than. So what does that mean? We know the probability that you choose one person that is female, it should be 0.8, okay? 80%, okay? But in this case, what we would like to find is that what's the probability, okay, that when we choose 25 people, what's the probability that it will be less than 60%, okay? Because it's less than. If I put down this, it means less than or equal to, okay? Less than or equal to, and less than is this, okay? So in this case, what do we get? It means we can have 14 people female, right? Can it be 15? No, because it has to be less than 15. So the same thing here. We put down the probability S, but it has to be less than 15, right? So what does that mean? That means it's less than or equal to 14, okay? So the same thing here. Since less than or equal to 14. So that means 14, 13, up to 0, because you can have 0 female in this case, right? So S will be equal to 0, and from 0 to 14, okay? The same thing here, you have 25 persons. You choose from 25 persons. Among them, S is female, and 0.8 to S power, 0.2 to 25 minus S power. So that would be the answer to these questions. Okay, then what about here? So the proportion of female is between this number and that number, okay? The same thing. Let me erase this part. So what does that mean? That means S divided by 25 must be less than or equal to 0.92, right? And this one is 0.68, okay? So then S must be equal to, let me try to figure this out. So it should be 23, right? It should be 23. So S is less than or equal to 23, and this one less than or equal to 17, right? Okay. So then in this case, the same thing. Probability of S less than or equal to 23 and greater than or equal to 17, okay? It should be S starting from 17, right, and to 23. And so what do we have? We have 25, choose 25, okay, and then 0.8 to S power, 0.2, 25 minus S power, okay? So basically, it is quite simple, okay? You just use this kind of binomial distribution, okay? You need to get familiar with all these formula, okay? And then just answer the questions. Any questions? Okay, if there's no question, we're going to continue to the next part. In this case, okay, we say that if the number of sample is large enough, then the binomial distribution actually can be approximated by normal distribution. In this case, we don't have a big sample. The number of sample we have is 25. So for the sample to be big enough, to be large enough, it has to be, the sample size has to be greater than 30, okay? If the sample size is greater than 30, we can use normal distribution to approximate the value of binomial distribution. And now we are going to talk about the theorem behind this application. Okay? It is called central limit theorem. What does central limit theorem tells us? Is that it doesn't matter what kind of distribution the population is. So the distribution of the population may be binomial, may be normal, maybe any other kinds of distribution, but it doesn't matter. If the sample size, okay, is greater than 30, then what you get? You get sample mean, and sample sum distribution will be approaching normal distribution. So basically, it's very easy. Whatever you get, it doesn't matter in terms of the population, okay? As long as the sample size you get is large enough, in this case, greater than 30, then the sample mean and the sample sum distribution will be normal distribution. And now let us look at one example here, okay? So, okay, so we have this. Suppose x and f. So x is equal to 1, 2, and 3, okay? And fx is in terms of, this is probability, okay? Probability of x is equal to 1/3. Probability of x equal to 2, also 1/3. And the same thing, 1/3 here. So what kind of distribution is this? This is uniform distribution, right? Uniform distribution. Because the probability for each number is the same, 1/3, 1/3, and 1/3. So in terms of diagram, we know it's like this. Right? So the probability distribution, if we draw a diagram, is something like this. This is x, this is fx, and this is 1/3, okay? But now we want to choose two samples, okay, with replacement, okay? We take one from this and put it back again, and then take one more and put it back again. So it is sampling with replacement, okay? Sampling with replacement. Then how many possibilities do we have? Because the first one can be 1, right? The second one can be 1, 2. Because we say we take one sample and we put this back, okay? And then choose one again. So we choose two samples, okay? Choose two samples. And we sampling with replacement, okay? So the first one can be 1, and then it can be 1, 2, or 3, right? So the same thing again. The first one can be 2. We choose 2. What about the second one? The second one can be 1, 2, or 3, right? And then the first one can be 3, okay? Also, the second one can be 1, 2, or 3. So in this case, how many different samples do we have? We have 9 different samples. Remember, we say that, okay? If the population, the size of population is n, okay, and the sample is n, okay, the sample size is n, and we say sampling with replacement, okay, sampling with replacement. Then what's the number of different samples? It is n to n's power, okay? It's n to n's power. So in this case, we have a population size of 3, right? And what about the sample size? The sample size is 2. So how many different samples do we have? We have 9 different samples, okay? Okay, then in this case, let us first talk about the sample sum. Maybe we deal with sample mean, okay? Sample mean. Okay, sample mean, what does that mean? Because we have 2 samples, right? We have 2 samples. And sample, so let us say it is sample 1, okay, and sample 2. So the sample would be equal to, the sample mean will be equal to x1 plus x2 divided by 2, right? Okay? So let us try to figure out how many different possibilities here. So this one can be 2, right? So the sample sum, and then sample mean. The simple sum can be 2, 3, right? 2, 3, 4, okay? Here the same thing, but we get one different, that's 5, okay? And then another one we get 6, okay? So if simple sum is 2, 3, 4, 5, 6, what about simple mean? It should be 1, 1.5, 2, 2.5, and 3, okay? Okay. But then what about probability? Because if you have all these, right, you need to figure out what's the probability, okay? So now let us try to figure out what's the probability that simple mean will be equal to 1, okay? So what's the probability that the first one you get 1? 1/3, right? And what about the second one you get 1? 1/3. So what about this? It should be 1/9, right? But then 3, okay? For 3, you have several possibilities, okay? 1 is here, because 1 plus 2 is equal to 3, okay? And 1 is here, okay? So then, what's the probability that you get a simple sum 3, or in this case, it is the same thing as simple mean 1.5. What's the probability? It should be 2/9, right? 2/9. Okay, then it should be 4 now, right? 4 is here, okay? And then 4, right? And then 4, okay? So you have 1, 2, and 3. So you have 3 possibilities there, okay? The same thing, you should be able to check it, okay? Okay, so remember, this is the population, right? This is the population, and this is the simple mean or simple sum, okay? So the original distribution is a uniform distribution, but after we take 9 samples out of this population, right, okay, what do we get? We get something like this. Okay? This is the population, right? And this is a sample. So what do you get? This one is uniform distribution, but this one looks like this, okay? And suppose, okay, suppose you get this one close to infinity, but really it doesn't have to. As long as it's greater enough, so say greater than 30, okay? Then what do you get? The next one you get will be something like this, okay? So the more samples you get, it's closer to this kind of situation. And so as you get the sample, okay, very large, you get very large sample. So what does that mean? That means it's going to be something like this. And what is that? That's normal distribution. So this is a proof, okay? Not really the proof, but show you, okay, why central limit theorem is there. Because if you do the same kind of experiment, okay, you get more samples. Then originally this is a uniform distribution, right? But then it gets to this, you get sample size 2. So suppose you get more samples, then you will be something like this, and that will be a normal distribution. So this shows you the possibilities there, okay? So central limit theorem, okay, really works. This is one example to show that it works in this way, okay? Even though the original population is not normal, but as you get more sample size, it looks like this. You get more. You can do some more examples on your own. Say, you know, you get n equals 3 and then n equals 4, okay? whatever number you want to get, then you really will get, this is the final result. It will get to a very smooth curve, and it is a normal distribution when the sample size is really big. Okay, any questions? Let us get to another example here. Okay, so we cast a dice. Okay? If the number is 1, 3, then it is a success. Okay? Otherwise, it is a failure. Now we cast 54 times. Okay? And S is the number of success. So the first one, try to find probability of S is less than or equal to 20, okay, greater than or equal to 10. And then the second one is the proportion of success is less than. Okay, so the same thing, right? In this case, you have two ways to deal with it, okay? Now, because the experiment, okay, the sample size, now it is 54, right? And 54 is already large enough. We say, as long as it is greater than 30, we can use normal distribution to approximate the value. In the first example, we have the number of experiment is only 25, okay? We choose 25 people from the factory. In this case, we have 54, so we can use normal distribution. But let us talk about the binomial distribution first. As we know, if you cast a dice, you get 6 numbers, right? 1, 2, 3, 4, 5, 6. And in this case, if it is 1 or 3, okay, if it is 1 or 3, then we say it is a success. So what's the probability of success? It is equal to 1/3, right? Okay, so the probability of success is equal to 1/3. Okay, so we got this done. And now we are talking about this. The number of success will be 10 to 20, okay? So then probability of S greater than or equal to 10, less than or equal to 20, okay? First we need to know the number of experiment is 54, okay? We have 54 experiments. So we will choose 54, right? And from these 54, 20 to 10, okay, there will be success. So this will be a summation sign, right? Summation S from 10 to 20, right? And how many experiments do? We do 24. And we choose from these 24, the number of success is S, right? And so in this case, the probability of success is 1/3, okay? Then the probability of failure should be 2/3, okay? And that would be 54 minus S. So this is the answer we have. Any questions so far? Okay, then we want to use a different way to do this kind of problem, and then there will be normal distribution. Okay, so when the number of samples is large, okay, then we can use the normal distribution to approximate the binomial distribution. But in this case, we need to know the sample. I mean, we need to know the mean, and we need to know the variance. Okay. So what is the mean? If it is a binomial distribution, right? What is the mean? The mean is n times p, right? What is the variance? That's n times p times q. Okay? So in this case, b, that is a binomial distribution. Okay, n, how many? What's the number of n? N is 54, right? And what's the probability of success? That's 1/3. So in this case, what do we get? We get 54 times 1/3, okay? And then the second one is 54 times 1/3 times 2/3, okay? So then what do we get? We get the mean will be equal to 18, and the variance is equal to 12, right? Any questions? So since we get all these, then the next step is to use normal distribution, okay? Now we need to figure out what's the number there and there. And we need to change this number into a standard normal distribution, and also this one and that one. We will do that in next hour. Thank you. This example. So we are done with the first question, okay? We have found the probability of S less than or equal to 20, greater than or equal to 10. And for the second question, because now we want to use normal distribution to approximate the value of this binomial distribution. So let us find out what's the probability, the mean and the variance in this case. So since we know this is a binomial distribution, right? Binomial distribution, the mean is this and the variance is this. So we know the number of experiments, the samples is 54. Probability of success is 1/3, and probability of failure is 2/3. So in this case, we can get to this part. Okay? So in this case, we can use this okay, to find out the probability. But also we can use normal distribution to do this, okay, to get the probability there. But in this case, since this is a discrete random variable, right? But normal distribution is a continuous distribution. So when you use a continuous distribution to approximate the value of a discrete distribution, you need to do some adjustments. But in this case, we will forget about it. But remember, if you do that, you have to do some adjustments there. But in this case, we don't care too much about it. So let me just show you how to use normal distribution to approximate a value here, okay? Okay, the same thing is probability of S between 20 and 10, okay? But now, what we want to do, we want to use Z distribution. So you have to change S into Z, right? If you want to change S into Z, okay, then this is the number, right? So it should be 20 minus 18 and divided by the standard deviation, right? That's square root 12, okay? The same thing here, 10 minus 18, and you get divided by square root 12, okay? So this is one way to deal with it. And after we learn central limit theorem, right, there's another way to get the probability. But as I mentioned, here I did not do any adjustment here because one is continuous distribution, one is discrete. If you want to use a continuous distribution to approximate the value of a discrete distribution, okay, you need to do some adjustment. But here, I just forget about it, okay? But you need to check the book how to do it. Okay, then the second question here. So the proportion of success is less than 4/9, okay? What does that mean? That means we have done, okay, 54 experiments, okay? And the number of success is here, okay? It should be less than or equal to, it's just less than, right? So it should be less than what? 9/4, right? So what does that mean? That means the number of success you get must be less than 24, okay? So in this case, the same thing here, okay? There are two ways to deal with it. The first one, okay, probability of S less than 24, okay? So in this case, because it's less than 24, right? So it's starting from 23, 22, up to 0. Okay, so it's probability of S less than or equal to 23. Okay? So S will start from 0 and to 23, right? How many experiments? 54. And the number of success, S. Probability of success, 1/3. And probability of failure, 2/1, 54 minus. Okay? Okay, then let us try to figure out. This is one way. We use the binomial distribution. And now, what about if we're going to use normal distribution? Okay, so let us try here. The same thing, okay, the same thing here, but the difference is S less than 24. But now, what we're going to do, we are going to transform this distribution into a standard normal. So it is PZ less than 24 minus 18 divided by square root 12. Okay? Okay. Can anyone try to calculate this for me? If you've got a calculator, can anyone do this for me? Anyone get a calculator? So this will be PZ less than 6, right? And square root 12. Square root 12 should be about 3 point something, right? What's the number here? Can you speak louder? 1.738, is that right? Okay. Generally, you don't have to do it to this point because according to the table, how many numbers do you have? You only have 2 decimal points, okay, here, okay? And so, can anyone check the table and tell me what's the probability? Check the table and tell me the probability. Anyone got the number? I just want to remind you there's something you have to pay attention to. Can anyone tell me the probability there? What should be the probability? So it is 1.73, right? Okay, but this is Z less than this number, okay? So it is less than all these, right? So what you get, of course, is here from the table, right? This is what you get. But don't forget about this part, right? You have to add this part, okay? This is what I want to remind you, okay? You get Z less than this, okay? So it has to be this part plus this part. How much is here? How much is here? 0.5. Okay, good. Okay, so basically we have done another chapter. So now we want to get to estimation. Okay, estimation. Any questions here? Questions? Okay, we will get to estimation. Okay, we are getting to the point of inferential statistics. Okay, inferential statistics. What does that mean? We want to infer what's going on in the population from the samples. And so in this case, we want to use a tool, okay? What's the tool? What's the best tool? So in this case, we talk about several things. One is estimate. If this is pronounced as mit, estimate is a value, okay? If it is, then that's a noun, okay? If we say estimate, that's a verb, okay? And then we have one estimator, okay? So that's something we use to estimate the others, okay? So that's a estimator. Okay? And there are several things here because, of course, you want to use the best tool, okay? The best estimator. So the best estimator must be unbiased. Okay? It must be unbiased. If it is biased, then it's not a good one, okay? And the second one, the second characteristic is efficient. Okay? It has to be efficient. Let me show you what all these means in this chart. So let us say you want to practice shooting, okay, marksmanship, okay? In this case, when you shoot, of course you want to get to the target, right? So if you can get to this part, okay, that's the best, okay, that's the best. Or if you can do this, okay, it is bad, okay, it's bad, but not too bad, okay? So what does this mean? This means it is biased, okay, because it cannot get to the target. It is biased. But is it efficient? Yes, it is efficient because it is, when you get the value, right, it is all around here. So in terms of efficient, that's efficient. In terms of unbiased, this is biased. Okay, this is biased. Unbiased means of course bias means this, okay? So in terms of the estimator, this is the best, okay? This is not good, but still not too bad, okay? What about this kind? Okay, sometimes you get it, but sometimes you don't get it, okay? In this case, it may be unbiased, but is it efficient? No, it's not efficient, okay? And the worst one, of course, is that it never gets to the target, and also it's spread around, okay? And so now, of course, in statistics, we are only interested in two things. One is x bar, mu x, sx squared, and sigma x squared, right? So if you're going to estimate mu x, that's the mean of the population, what you're going to use? You're going to use sample mean, okay? If you want to estimate the population variance, what you're going to use? You're going to use sample variance. And now we want to show you, okay, why this is the case. Because this one is the best, it is unbiased. Okay. Before I go on, I would like to remind you we already discussed the properties of sample mean, sample sum. We say if X is a distribution with the mean mu X, the variance sigma X squared, okay, then what about the sample mean distribution? It should be mu X and n sigma X squared over n, okay? This is sample mean. And then we have sample sum, right? If X has a mean of mu X and variance sigma X squared, then S should be n times mu X and n times sigma X squared. Any questions so far? You should remember all these, okay? It will be on the test, okay? Okay, then of course, we say if this is an estimator, and it is going to, this estimator is going to estimate theta, okay? So this is the value, okay, you want to estimate. Of course, on average, you would like to have this number is equal to that number. So what does that mean? If theta hat, expectation of theta hat, less than theta is equal to 0, then we say theta hat is an unbiased estimator. Okay? If this one minus this one, the true value, is equal to 0, then we say it is an unbiased estimator. And now we want to show you X bar, okay, is an unbiased estimator, because what is that? The expectation is equal to mean, okay, is mu X. Let us try again. So we have expectation X bar, right, is equal to expectation of 1 over n summation xi, okay? Because this is exactly the formula, right? Then we can get this out. It's 1 over n, okay? Expectation summation xi, right? And you know this one is equal to 1 over n expectation x1 plus x2 plus xn. On average, what do you get? You get 1 over n, and this one you get mu x, and mu x. How many mu x do you have? You have n mu x. So 1 over n times n mu x. So what do you get? Mu x. So this is X bar is an unbiased estimator for mu x. Okay, X bar is an unbiased estimator for mu x. What about this? Okay, the reason we use Sx squared, of course, is the same thing because it is an unbiased estimator for this. Okay, so now let us try it. Okay, so we have expectation Sx squared is equal to what? Expectation 1 over n minus 1 summation xi minus x bar squared. Any questions so far? Because this is exactly this, right? This one is equal to that one. And so we get 1 over n minus 1 out. Okay, we get this out. And expectation, do you remember? As a matter of fact, this is equal to summation xi squared minus n x bar squared, right? Is that right? Okay. Now, what do we get? We get n minus 1, okay, expectation x1 squared plus x2 squared plus xn squared minus n x bar square. Okay? Now, the question is, still remember, do you still remember this? Okay, let me get... Okay, expectation x bar. What is this equal to? What is this equal to? It is equal to variance of x plus what? Mu x squared, right? The same thing. What about expectation x bar squared? If it is x bar squared, that would be variance of x bar, right? Plus mu x bar squared. Okay? In terms of notation, right? In terms of notation. This is x, of course, it's variance of x, mu x squared. But this is x bar, right? X bar, so it should be v x bar and mu x bar. But what is v x bar? V x bar is equal to sigma square over n, right? And mu x bar is mu x, right? Okay? Any questions so far? So now let's try, okay? So what do you have? So as a matter of fact, we know we have 1 over 1 n minus 1, okay? Expectation x1 square plus expectation xn square minus n times expectation x bar square, right? Okay? Any questions so far? Okay, then what do you get? Because in this case, this is equal to, okay, Vx, right, plus mu x squared, right? The same thing for each one, okay? How many do you have? You have n, okay? You have n. And in this case, as a matter of fact, you know, Vx, okay, Vx, variance of x is exactly sigma x squared, right? So 1 over n minus 1. Here you have n sigma x squared, right? Plus n times mu x squared. Okay? Any questions up to this point? Because we know this one is equal to Vx plus mu x squared, right? And variance of x is sigma x squared. How many do we have? We have n. So this will be n times sigma x squared plus n times mu x squared. Okay, the same thing here. Because in this case, expectation of x bar squared is here, right? Okay, this one is here. So n times n times sigma x squared over n, what do we get? We get sigma x squared. And n times mu x squared, you get minus n mu x squared. Okay? So in this case, this one and this one, you got cancel out, right? And how? So that's here. So that is 1 over n minus 1 times n minus 1 sigma x squared. And that is exactly equal to what? Sigma x squared. Okay? So you get it? Here you have n times sigma x squared, and here you have minus 1. So you got n minus 1 there. And n minus 1, you get cancelled out. So sigma x squared. So x bar is an unbiased estimator of mu x. What about xx squared? The same thing. It is an unbiased estimator for sigma x squared. So that's the reason, okay, when you use sx squared, it has to be divided by m minus 1, not n, okay? It has to be divided by m minus 1. That's the reason we use it. Okay, any questions so far? So let us move on. There are some other kinds of property, okay? So the first we get this. Choose a good estimator, okay? First you have to choose a good estimator. There are some other kind of properties like consistent. And sufficient, okay? There are a lot of other properties that we can talk about it. Also, maximum likelihood. Maximum likelihood. There are a lot of methods there. But in this case, we simply don't have that much time to talk about it, okay? So we will all forget about these parts. The textbook talks about this a little bit. So if you have time, read it on your own. We simply have limited time. We don't have time to discuss all these issues, okay? So what will be the next? The next one is about estimate, okay? When we estimate, okay, there are several ways to estimate it. So when we estimate the population mean or population variance, of course there are several ways to estimate it. And also there are some issues here, okay? Generally, if you want to get a number, so let us say we get Thai plastic, okay? If you have read the newspaper, you know Thai plastic, okay, they have, Thai plastic, they have a lot of good news this year, okay. The revenues is quite good, and also the profit margin also increases. And so now, if someone gonna ask you, so let us say later on you get a job as a financial analyst, okay, financial analyst of a company, okay, stock company, and then you want to tell your customers, okay, the investors, how much will be a good buy. So of course in terms of stocks, how can you make money out of stocks? You buy low and sell high, right? Buy low and sell high. And so in this case, you may have questions. So let us say Thai plastic, the price now is $60 per share. Okay, let us say it's $60 per share. But is this a good point to buy? Is the price too high? Is this price good enough? So of course, when you buy the stock at $60, what you expect? You expect the price going to get higher, 61, 62, and then sell that to get a profit, okay? But the question is this price high enough? So you have to estimate, right? So sometimes later on when you get a job as a financial analyst, what you get? You have to calculate all the historical prices, okay? So from the performance of the stock in the past 1 or 2 years, of course, then you get a lot of price ranges, okay? And from there, you get what? You get mean, right? You get the average price. And of course, in that case, you know the variance, okay? How widespread is the price, okay? You also get the variance. But now, as you have known, if you read the newspaper, a lot of reporters or financial analysts, they say this is a low point, okay? The price or the probability for this price to go up is high, okay? Sometimes people say that. And sometimes people say, you know, what you expect in the future of the price range, it may be 65 to 80. So let us say this. Now the price is 60, but say you are the financial analyst, according to the data, what you find? It is quite possible that it will get 65 to 80. So in this case, will people buy it? According to your advice, people will buy the stock, right? Because now it is $60, okay? And it may be able to get to 65 or even 80. But of course, you may be wrong, right? You may be wrong because, and of course, if you are wrong, then it hurts your reputation, okay? Reputation. Okay? If you say something wrong, a lot of times people simply don't trust you, right? So in this case, you want to figure out something. So if say, okay, the price is going to be 65. So let us say you do this. And what is this? This is a point estimate. Okay, this is a point estimate. You only give people one price. I say, today the price should get to $65. Okay? This may happen, it may not happen. The probability is 100% or 0, right? Either you get it or either you don't. So in this case, it doesn't help you. So oftentimes, what you want to get people is to give them a range. Okay? You give them a range. So in this case, it is a higher probability that this can happen. Okay? This may happen. Okay? And of course, according to our theory, right, we can show you that, as a matter of fact, you can base your estimate on probability theory. Okay? So later on you can show people, right? As a matter of fact, this will happen at a certain probability, okay? And of course, if the range is higher, so let us say 50 to 90, okay? Because the probability that the stock price can hit 65 to 80, of course, it is already big. But if you give people a number like this, the probability it will happen is even higher, right? But let us say you have a confidence interval. So this is an interval, right? If this interval is too large, then it doesn't make sense, okay? So let us say if you tell your customer, so the stock price of Thai plastic will be between 0 and 100. Does it make sense? It doesn't make sense because, of course, it's like this. What I want to know is that now the price is 60. How close are you going to be? Say 70, 75, and what's the probability? So oftentimes, this is the way we deal with all these numbers, to tell people the price range of a stock or for whatever case that people are interested. For example, next year we're going to have a presidential campaign, right? And of course, Mr. Chen and Mr. Lian, of course, they are worried about, okay, what's the probability they're going to be elected. Of course, they need to look at poll. What is poll? Okay? They need to look at a poll. But is the poll 100% correct? No. They have to estimate. The same thing, they get a sample, right? And from the sample, they try to infer the population. They sample, say, 2,000 people, 5,000 people, and they try to figure out from these 5,000 people what the other people are thinking about. The whole population, what are they thinking about, right? So the same thing, we need to have all these tools, okay? And basically, let me tell you what's the idea there, okay? And then we need to talk about two terms. One is confidence interval, and the other is significant level. Okay? If the confidence interval is 1 minus alpha, okay? If the confidence interval is 1 minus alpha, then the significant level is alpha, okay? Oftentimes it looks like this. So suppose it is a normal distribution. Of course, you're going to get a mean like this, okay? So from here, you want to estimate what's going on in terms of the population, okay? And the estimation is within certain region. So when we say 1 minus alpha confidence interval, as a matter of fact, what do we mean by this? It means the probability it will happen is 1 minus alpha, okay? When we say confidence interval 1 minus alpha, right? As a matter of fact, what we mean is that the probability that this true value will be in this value, the probability is 1 minus alpha. Of course, it may happen, it may not happen. What's the probability that this will not happen? It will be alpha over 2, alpha over 2. So the probability it will happen is 1 minus alpha. But of course, this is not 100% correct because there is a probability that it won't happen. What's the probability that it will not happen? Alpha over 2, alpha over 2. Okay? So now, in terms of the formula, how do we get that? Okay? So P, Z. So there are two regions, right? This one should be Z alpha over 2. And this one should be Z alpha over 2, right? But this is on the right-hand side. This is on the left-hand side. So what should be this? This is a negative number. Okay, this is a negative number. So we know alpha over 2, Z, right? And Z. We know this probability is equal to 1 minus alpha, right? Okay, this probability is equal to 1 minus alpha. Any questions up to this point? Okay, and then what is Z? Z is equal to x bar minus mu x divided by this, right? Okay, Z is equal to this. Okay, and then the same thing here. Okay, so now let me get rid of this part because we already know the probability is 1 minus alpha. Okay? Okay, then let's try to simplify this. It should be P Okay, any questions so far? Because we want to get rid of this, right? We get rid of this, we multiply this by this, okay? This is the standard deviation of the x bar, okay? Standard deviation of x bar. And then we get this. Okay, so now let us try to rearrange this. If we multiply negative 1, okay, if we multiply negative 1 here, so it should be now mu x minus x bar, right? Okay, multiply it by this, okay? But you want to be careful here. So let us say 3 is less than or equal to 4, less than or equal to 5, right? Okay, 3 less than or equal to 4, less than or equal to 5, right? If we multiply it by negative 1, what does that mean? That means negative 5 less than or equal to negative 4, less than or equal to negative 3. So you have to change all these, right? So then, in this case, this one multiplied by negative 1, it becomes positive, right? Becomes positive when you move here. And this one, you multiply it by negative 1, what do you get? You get negative, right? And it should be here. So basically, you don't change anything, right? Okay? Okay. Any questions so far? So this is what you get. And now that's the reason we say we can use this confidence interval here, because, okay, what you get? This is x bar, right? If you add x bar here, you have to add x bar here and there, right? If you add x bar, so we add x bar there. Oh, sorry, it should be negative, right? So it should be negative. Minus z alpha over 2 and sigma x squared over n minus less than or equal to mu x and x bar minus plus z alpha over 2 and this. Okay, so what does that mean? It gives us the theory, okay, behind this confidence interval. Okay, so if you are required to estimate the true value of the population mean, okay, what you get? You get, if you know x bar, okay, the right hand limit will be x bar plus this, and then the right hand, the left hand limit will be this, and the right hand limit will be that. So later on, if you are required to get an estimate, okay, for the population mean, and you want to use confidence interval, in this case, what you're going to get? You get x bar minus plus minus z alpha over 2 and this sigma x squared over n. So this is the confidence interval or the interval estimate for the population mean, okay? Because in this case, you know, the true value of the population mean will be between this number and that number. And what's the probability that this number will be there? It is 1 minus alpha, okay? So this is interval estimate, okay? Interval estimate for the question here. I think let us stop here. Take a break.